In the first two modules, we have discussed topological spaces and basis. We have given various examples of topological spaces. We have seen that whole R with usual topology. We have seen that R2 is a topological spaces. Similarly, taking open solid ball as basis, we can say that R3 is a topological spaces. Similarly, taking open solid balls, n dimensional balls, we can say that Rn is a topological spaces. But how we can say that any open interval, any finite open interval is a topological spaces, or a circle in R2 is a topological spaces, or an open disk or closed disk is a topological spaces, or a sphere a topological spaces, or a torus is a topological spaces. In generally, if we take any subset or any interesting geometric figure in R3, is it a topological spaces? For this, we now introduce some method which will help us to get new topological spaces from old topological spaces. First, we introduce the notion of subspace for this purpose. In this chapter, we deal with constructing new spaces from old ones. So, our first step is to give a topology on subset of a given topological spaces. So, let us consider X be a topological spaces with the topology script O, and let A be subset of X. We would like to use the topology on X to define a new topology, say OA on A. There is an easy way to do this, taking the trace of open sets in X on A. Just define a set O subset of A to be in OA if there exists an open set O dot in X such that O is equal to O intersection O dot. But first we have to prove that OA is in fact a topology. So, let us say this proposition. Prove that OA is in fact a topology on A. Since empty set intersection A is empty, so empty set certainly belongs to OA. Now, A intersection X is A, so A belongs to OA. The fact that it is closed under finite intersection and arbitrary union follows from the following equations. U1 intersection A intersection U2 intersection A continuing UN intersection A is equal to U1 intersection U2 intersection continuing intersection UN intersection A, and union alpha belongs to J in U alpha intersection A is equal to union of U alpha, alpha belongs to J intersection A. From these two equality, from the first equality we can prove that OA is closed under finite intersection, and from the second we can prove that OA is closed under arbitrary union. So, OA is a topology on A. With this topology, OA will be called subspace of XO. For example, let us consider an open interval 0, 1. So, what will be the subspace topology of R on closed interval 0, 1? No, so, subspace topology will be given by the intersection of open sets of R with the interval 0, 1. That means open intervals in 0, 1. So, in the subspace topology on 0, 1, the basic open sets are the open intervals of 0, 1. Let us say something about metric space. A topological space will be called metrizable if if there exists a metric on that set X such that the topology generated by open ball as basis equals with the original topology of X. So, thus we can define a metrizable topological space. Now, we already know that if we have a metric space and let Y be a subset of the given metric space X. Now, if we restrict the metric on the subset, then we get another metric space. Now, this is the question. Let tau be the topology generated on X generated by the metric D, say. Now, let Y subset of X and consider the restricted metric on Y as rho. Then rho generates a topology on Y. So, whether subspace topology on Y and this topology are equivalent, it can be proved that these two topologies are equivalent. Proposition: the metric topology on a subset A of a metric space X is the same as the subspace topology. Proof: observe first that for a ball BRX in capital X, the intersection A intersection BRX consists of all points in A of distance less than r from X. So, this is a ball in A regarded as a metric space in itself. For a collection of such balls BRX, we have A intersection union of BR alpha X alpha is equal to union of A intersection BR alpha X alpha. The left side of this equation is a typical open set in A with the subspace topology, and the right side is a typical open set in the metric topology. So, these two topologies are equivalent, these two topologies coincides. Open and closed subspace. So, we have defined subspace of a topological space. Now, let A be a subset of X which is open, then it will be called an open subspace, and if we take O as closed, then it will be called closed subspace. However, we have the following fact, the easy proof is left to the readers. For a subspace Y subset of X which is open in X, a subset A of Y is open in Y if and only if it is open in X. Respectively, if Y subset of X is closed, then a subset A of Y is closed in Y if and only if it is closed in X. Now, let us put this example. Give an example of a topological space to establish that open or closed for the subspace Y in the above lemma cannot be removed. What can be the answer? Consider the closed interval 0 1 in RU. Semi open interval, left side open, right side 1 is open in the closed interval 0 1 in the subspace topology, but not open in RU. This happens because closed interval 0 1 is not open in RU. So, though 0 1 is open in closed interval 0 1, but this is not open in the RU, closure of subspace. The following theorem shows that closure behaves nicely with respect to subspaces. Theorem: given a space X, a subspace Y and a subset of y, then closure of A in the space Y is the intersection of closure of A in X with Y. That means closure of A with respect to Y is equal to closure of A with respect to X intersection Y. That is, a point Y belongs to capital Y is a limit point of A in Y, that is, using the subspace topology on Y, if and only if Y is a limit point of A in X. Let us come to the proof. For a point Y belongs to Y to be a limit point of A in X means that every open set O in X that contains Y meets A. Since A subset of Y, this is equivalent to O intersection Y meeting A, or in other words, that every open set in Y containing Y meets A. I am asking the student to show by an example that analogous statement of the above theorem is not true for interiors as well. Now let us come up with some exercise. Prove that the subspace topology on Z induced from R is discrete. In fact, if we take some point, say n belongs to Z, let us consider the open interval n minus half, n plus half in R. Then if we take n minus half comma n plus half the intersection Z, then we get just the singleton set n. So, singleton set n is open in Z. That means every subset of Z is open. So, subspace topology on Z induced from R is discrete. We can also prove that subspace topology on Zn induced from Rn is discrete. This can be proved in analogous way. Let us consider Z2. Let us take a point xy belongs to Z2. Then xy also belongs to R2. Let us consider a rectangle in R2 containing xy which does not containing any point whose coordinates are integers. Then this rectangle intersection of this rectangle with Z2 is just singleton xy. So, singleton xy is an open set in Z2, that means each singleton is open set in Z2. So, the subspace topology on Z2 induced from R2 is discrete. Similarly, we can prove that for any n, subspace topology on Zn induced from Rn is discrete. Let us prove the following theorem. Let X be a linearly ordered topological space and Y be a subset of X that is convex in X. That means if x y belongs to Y and Z less than Y greater than X, then Z also belongs to Y. Then the ordered topology on Y is the same as the topology Y inherits as a subspace of X. The proof is easy. I am omitting the proof, but I am asking the student to produce an example to show that convexity cannot be removed in the above theorem. You can consider Z in R. So, what is the subspace topology on Z in R? We have seen in the previous example that the subspace topology on Z induced from R is discrete. But if we take the order topology on Z, then no singleton is open. Please check it. So, the subspace topology induced from R and the ordered topology on Z are different. Let us come up with an interesting example. Let L be a line, a straight line in the plane, and let us consider these two topological spaces, RL cross R and RL cross RL. So, what is the topology on RL cross R and RL cross RL? Taking the rectangles, we get the topology of RL cross R or RL cross RL. That means, taking Cartesian product of open sets, we get the topology of RL cross R and RL cross RL. In each case, we get a familiar topology. What are those? In the last slide, we have considered example of topological spaces RL cross R and RL cross RL and a subset which is a line there. In fact, it could be better if we introduce this example, if we give this example after discussing product topology. But for the necessity, we have discussed it here. So, for better understanding of student, let us describe what is called finite product topology in 2 or 3 terms. Let X and Y be two topological spaces. If we take all possible Cartesian products of open sets of X and Y, that is U cross V, such that U is an open set of X and V is an open set of Y, then this gives a basis on the set X cross Y for some topology. This topology is called product topology on X cross Y. Here, in the above examples, we have considered this topology. So, in the first example, RL cross R, if we consider the line as shown in the diagram, the subspace topology is the topology of the lower limit topology, and in the example shown in the right side, the topology is discrete. Now, let us consider some examples of subspaces. We have already mentioned that circle is contained in R2 is a subspace of R2. So, we can describe circle as the following said, e to the power 2 pi I theta, where theta less or equal to 1 greater than 0. So, which are open sets of circle? We know that open sets of R2 means open disk, or open disk is the basis of the topology of R2. Now, what happens if an open disk meets a circle? We just get an open arc. So, open arcs are the basis of the circle. Now, let us come to important example of sphere. Sphere is in R3, in fact, the collection of all points of R3 which are in a distance 1 from the origin. So, what are the open sets of a sphere? As sphere is a subset of R3, we have to intersect sphere with open sets of R3. So, what are the basic open sets of R3? We know that basic open sets of R3 are open solid balls. So, what happens when a open solid ball intersects a sphere? In the first figure, show that you can see that when a open solid ball intersects sphere, what we get? we get a disk such that a disk which is slightly curved. In the second example, and what happens if a open disk meets sphere, we have seen that we have got an upper part of the sphere. So, these are the basic open sets of the sphere. Now, let us come to another example. This example is called torous. How we get it? Let us consider a rectangular piece of paper. Now, let us identify left side and right sides. Then what we get? We get a cylinder or tube. Now, we identify both sides which are open of the tube, then we get a shape like a tube. This is called torus. Torus is an extremely important geometrical object. We are not giving now descriptive description of torus, but what are the open sets of the torus? Again, we will get open sets of torus by taking intersection of open solid balls of R3 with the torus. This figure is called figure 8. This is an extremely important example. You can see that this is a subset of R2. So, what type of open sets have figure 8? In fact, to get open sets of figure 8, what we have to do? We have to intersect figure 8 with open disk of R2. What kind of figure we can get? If some open disks intersect say in the left side, then we will get an open arc, or some open disk intersect in the right side, we will get again an open arc. But if an open disk intersect in the middle, what we get? The picture in the right side. So, these are some basic open sets of figure 8. So, we have already discussed about finite product topology in our previous video. Now, we are going to formally define finite product topology. Again, the motivation to discuss product topology is to get new example of topological spaces from old one. For example, there we have got RL cross R as a new example of topological spaces, RL cross R as a new example of topological space. In R cross R, we have considered open disk as open sets, but we have already told that rectangles are open sets or basic open sets of R2. How it comes? It comes through product topology. So, we have to formally define product topology. Let X and Y be two topological spaces. We can define a topology on X cross Y by saying that basis consists of the sets U cross V, as U ranges over open sets in X and V ranges over open sets in Y. In the next theorem, we shall show that it is sufficient to consider basic elements also. Let X, Y be two topological spaces with basis script B and script C. Consider the collection script B Cartesian product script C is equal to U Cartesian product V such that U belongs to script B and V belongs to script C. Then script B cross C is a basis for the product topology on X cross Y. The first condition for basis is obvious. Now, let U cross V and M cross N be in script B cross C, and let X Y belongs to U cross V intersection M cross N. Then there exists A belongs to script B and B belongs to script C such that X belongs to A subset of U intersection M and Y belongs to B subset of V intersection N. Therefore, XY belongs to A cross B subset of U Cartesian product V intersection M Cartesian product N. Hence, script B cross C is a basis. Now, to show that it generates the product topology, let XY belongs to U cross V, where U is an open set of X and V is an open set of Y. Then it is easy to prove that U cross V is an open set with respect to the basis script B cross C. So, this proves that it is sufficient to consider basic open sets to define product topology. We conclude this section by defining projection map. So, what is projection map? Let x1, x2, xn be n sets, non-empty sets, and let X be the Cartesian product of x1 cross x2 cross xn. Let us define a mapping pi I from the Cartesian product x to xi in this way: pi I of x1, x2, xn is equal to xi. That means pi I maps the element x1, x2, xn to xi. This mapping is called ith projection map. It will be important for our purpose. So, the crux of this module is that formation of subspace and formation of product topology. With the help of subspace, we can create so many new spaces from old one. For example, circle, for example, sphere, for example, torus. And with the help of product topology, we know that R cross R or R2, R3, in general Rn are topological spaces, though we can consider them from the metric space view, but we can consider them as product topological view also. With this, we conclude this module.